Welcome to our 36 Combinatorics lecture. Today we'll talk about matchings and we'll discuss other applications of Hall's marriage theorem. The first application that we'll talk about involves doubly stochastic matrices. So first, let's give a definition of such a matrix. So let's say we have a natural number n. Then we have a matrix A. Those entries are aij for I and j between 1 and n, with aij non-negative, so real and non-negative. Then the matrix A is called doubly stochastic if the sum of each row and the sum of each column is 1. So if the entries in each row, each column, sum to 1. Okay. So such matrices are of great interest in probability theory, for example. And let's give some simple examples. I mean, the identity matrix IN is a doubly stochastic matrix. Actually, any permutation matrix is a doubly stochastic matrix. So permutation matrix, as you recall, is a square matrix, which is a 0, 1 matrix, and such that in each row and each column they're exactly 1, 1. But there are other, doubly stochastic matrices. So here's some example of a 4 by 4, 2, 3, 0, 0.4, 0, 0.1, 0.6, 0, 0.1, 0. So it can be checked that the sum on each row. So if you pick, for example, this row, it's 1, and the sum on each column is also 1. Okay, so this is a doubly stochastic matrix. Now, here's the result that we are going to prove. And this is a theorem which is commonly referred to as the Birkhoff-von Neumann Theorem. I think Garrett Birkhoff was an American mathematician. He proved it around 1946, and I think independently John von Neumann proved it around 1953. And the theorem is the following: every doubly stochastic matrix can be written as a linear combination of permutation matrices. Okay. Actually, we'll prove a form that is equivalent to it. I mean, it makes it easier for when we do the induction step, and we'll prove something of the form every square real and non-negative matrix whose row or column sums are the same can be written as a linear combination of permutation matrices. So if you call the first one theorem 1 and the second statement theorem 2, it's not too hard to see that they're equivalent. Well, clearly theorem 2 implies theorem 1 because theorem 1 is clearly a generalization of theorem 1. And now if you know theorem 1, then how can you prove theorem 2? Well, if you take a matrix, let's say whose rows and column sums are, let's say 100, then you just divide all the entries of that matrix by 100 and you get a doubly stochastic matrix. And what you have is that your original matrix is 1 over 100 times a doubly stochastic matrix, which by theorem 1 can be written as a linear combination of permutation matrices. And that does the proof. So we'll prove theorem 2. Sometimes this happens in mathematics. You prove a generalization or an extension of a result, makes it a bit easier to actually prove the result. In this case, I mean, it doesn't matter. They're equivalent. So what we'll do is we use strong induction on the number of non-zero entries in our matrix. Okay, so let's say, what is the, where do you start with this strong induction? So let's say we have our square matrix, let's call it A, and so each row, each column, let's say, sums up to 1. So therefore, in each column, there's at least one non-zero entry. So that's true for each column, at least one non-zero entry. Therefore, if A is a doubly stochastic matrix, A is, let's say, a doubly stochastic matrix, implies that A has at least n non-zero entries. Now, when do you get equality? Well, you get equality if you have in each column exactly one non-zero entry. So that means that that non-zero entry must be a 1. And in order for A to be doubly stochastic, those ones have to be in different rows as well. Therefore, A must be a permutation matrix. Okay, so this simple observation allows us to start the base case. So the base case for our induction, for a strong induction proof, is n. So the number of non-zero entries in the matrix is so let's spell it out better, is when the number in our matrix. So, but by the previous observation, this is the same as A being a permutation matrix. And the permutation matrix is a linear combination of other permutation matrices. So the base case is true. Okay. I guess I didn't write here, but it should be obvious that what does it mean that a matrix A is a linear combination of permutation matrices? You can write A as something like C1 permutation matrix 1, and so on, plus CT times the permutation matrix PT for some t greater or equal to 1 and some real number C1 CT. Okay. Now for the induction step, assume that A is a doubly stochastic matrix with whose number of non-zero entries is at least m plus 1. Now, the idea of the proof is the following. So we have this matrix. Think about it like the matrix that I gave you here, this 4x4 matrix. So you have a matrix like that. So you see in some positions you have zeros and so on. So what we want to do first is we want to find a transversal in this matrix. So what is that? It's we want to pick from so we want to pick some entries of the matrix such that we pick one entry from each row and each column, such that those entries are positive. So for example, we wouldn't be able to pick 0, 2, 0, 2, 0, and 0, 1 because this entry here is 0. So we want to avoid that. But we could pick 0, 2, 0, 4, and 0, 1. This would be okay. We have one entry from each row and each column, and the entries in the matrix, the entries that we pick are all positive. So that's the first thing that we want to show, that we can do something like that in the graph, in our matrix. So if we come back here, we have a little claim, which will start our induction step proof. Is we claim that we may select n non-zero entries of our matrix of A, such that each row and each column contains exactly one of these entries. Now here the notation will be a little bit different from the notations in our previous lectures, where we denoted the color classes or the partite sets of the bipartite graphs by A and B. Here we have A as the number of as a matrix. So I need a, when I define a bipartite graph, I will need different letters for the partite sets, but that shouldn't be too confusing because this is the way. So I will define in order to use Hall's marriage theorem, we have to create a bipartite graph. And so the bipartite graph that we'll create will be in terms of this matrix. So we have our matrix A, and let's say we have some row here, row I, and we have some column here, column Cj, and they meet at this entry here, which is Aij. So the graph will be as follows. We have the partite sets will correspond to the rows of A, and the other partite set, let me has a different color, will correspond to the columns of A. Now, how does this work? Well, we have here row 1, row 2, row I, all the way up to row N. And on the other side, we have column 1, column 2, column J, all the way up to column N. And we put an edge between row I and column J, if and only if the entry in that of the matrix in the position in the row I and in the column J is positive. So that's how it works. Okay. So any matrix, but in this case it's a square matrix. So this square matrix A with n rows and n columns can give us a bipartite graph with partite sets each of size n, one partite set corresponding to the rows and one partite set corresponding to the columns, such that in the there is an edge between row I and column J if and only if the entry in the position ij of the matrix is positive. So if we go back to our example here, so let me draw this graph over here. We have row 1, row 2, row 3, row 4, and we have 4 columns, column 1, column 2, column 3, column 4. And what are the edges? Well, if you look on the first row, all the entries are positive, so row 1 is adjacent to everybody else. On the second row, there's a 0 entry in the position 3, so row 2 is not going to be adjacent to column 3, but it's adjacent to column 1, column 2, and column 4. Row 3, there's a 0 in the position 3, 1, so there's no edge between row 3 and column 1, but there are edges between row 3, column 2, and column 4, and row 4 has edges to everybody else. So it's a very dense graph. It's essentially complete bipartite graph K44 minus 2 edges corresponding to these 0 entries. Okay, and now what I want you to notice, this is the key fact here, is that if I look at this transversal that I have in purple, where I have the entries, one entry from each row and each column that is positive, that if I look at the edges corresponding to these entries, they form a perfect matching in this graph. So those edges will be, let me draw them separately. Over here will be something like, if I have this drawn in purple, will be row 1 goes to column 3, row 2 goes to column 4, row 3 goes to column 2, and row 4 goes to column 1. So with the same notation, this would be row 1, row 2, row 3, row 4, column 1, column 2, column 3, column 4. Okay. So this transversal, if we go back here, so this our claim that we may select n non-zero entries from A. So non-zero, not actually means positive entries of A, such that each row and each column contains exactly one of these entries. This assertion is equivalent to this graph. Let's call it gamma. Let's call it gamma. It's equivalent to this graph. Gamma has a perfect matching. And that's what we want to prove. If we want to prove the claim, it's equivalent to gamma having a perfect matching. And we will prove that gamma has a perfect matching using Hall's marriage theorem. So how do we do that? Well, okay, again, let me use different colors as before. we have our set of rows here. And we have our set of columns. So to prove this, so we use Hall's-Marriage theorem. So we have to verify, in order to use Hall's-Marriage theorem, we have to verify that Hall's condition is satisfied. So Hall's condition, it's that for any S, the subset of vertices here is on the row set, a subset of rows. The neighborhood of this set S has cardinality at least the cardinality of S in this graph gamma. Okay, so we take here some subset S. Okay, so we have some rows in this subset. Let's say cardinality of S equals S. If you want to think in terms of the matrices, that's also helpful here. So we have this square matrix, and we can pick a subset of S of these rows. Now, these rows, they don't have to be consecutive like I draw them here, but just for the sake of a picture, it's easier to draw them that way. So that's a subset of rows. Now, what is the neighborhood of S? So then by the definition, the neighborhood of the set of vertices N of S, let's write in terms of columns, consists of all these columns Cj, such that Cj is adjacent to some row I for some row I in the set S. But what does it mean Cj is adjacent to row I? That means it's the same thing that the entry Aij is positive. Okay, so the neighborhood, when we look at the column, so let's say we will have two types of columns. If we look at the column here, let's say this is some column Cj, and anywhere in one of these entries we see something positive, then that column is part of the neighborhood of S. Okay, but if we look at the column and we see everything as 0, 0, 0 in that column is not in NS. Okay, so all these columns that are not in the neighborhood of S, they have 0 everywhere. Okay, so now what do? Well, we focus on this matrix. We focus on this submatrix here. So this is the submatrix of A corresponding to the rows in S and the columns in NS. Now, if you look at each row in this matrix, it doesn't have to have all entries positive, but definitely has at least one positive entry. But one thing for sure is that outside of this row, all these entries on that row, all the entries are 0. So because the sum of the original row of the matrix A was 1, it means that the sum of each of these rows is going to be 1. So in this smaller matrix, let's write it here, each row sums to 1. So therefore, the total row sums, so the row sums, the sums of all the rows will give us cardinality of S, which is S. Okay. Now, if we look on a column, So if you look on a column, what we picked here, we picked a subset of that column, and we know that the whole column sums up to 1. So the subset of the column is going to sum up to something that is less than or equal to 1. So each column sums to at most 1. So it could be 1, but it's 1 or less. So therefore, if you do column sums, we're going to be that this is less than or equal. How many columns we have? It's the cardinality of ns times 1. So if you put these two things together, the sum of all the entries in the matrix is both the row sums and the column sums. So that gives us that the cardinality of S is less than or equal than the neighborhood, the cardinality of the neighborhood of S. So that means that Hall's condition is satisfied, and that means that the graph has a perfect match. Okay. So the key here was that in this sum matrix, so in this sum matrix, all the rows actually have sum exactly to 1. So if we put here the neighborhood of S, its cardinality is greater than the cardinality of S. Okay, so I hope that's clear. So Hall's condition is satisfied. We have a perfect matching. Okay, so how does that help us? Well, let's see how it did help us on this concrete example here. So let me erase here. Okay, so what we could do here is we have our matrix A. We look at these entries in this transversal, and the smallest of them is 0.1. So we create a permutation matrix, let's call it P1, in which we put corresponding to these non-zero entries that we found. Okay, this is a permutation matrix P1. And then we take C1, we define C1 as the minimum of all these entries in these positions, which is 0.1. And so then what we do from our matrix A, we subtract C1 times P1. And what does this do? Well, it will lower the row sums and the column sums by 0.1. And now they change and they become 0.2, 0.3. And in this position 0.4, it becomes 0.4 minus 0.1. So it's 0.3. And then we get here 0.1, 0.6, 0.3, 0. And now we've created another 0 here. So we created another 0. And then we have 0 here. The entry drops by 1, so it's 0.1, 0.5, 0.3. And the last one, last row, 0.1, 0.2, 0.1, and 0.5. Okay, now the matrix that we have is also a matrix which is real, non-negative. It's a square matrix and has constant row sum and constant column sum. So the same sum for each column and each row, and that's sum equals 0.9 in this situation. But the other thing is that the number of non-zero entries in this matrix is smaller than it's smaller than the number of non-zero entries in A. So by the induction hypothesis, here you apply the induction hypothesis. This matrix can be written as a linear combination of permutation matrices, C2 times P2 plus blah, 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 plus CT times PT. And then when we move C1 times P1 to the other side, it gives us the required result for A. Okay, so that's the idea here. So we have this this transversal with all these positive entries on them. So what that means is that we can, using the transversal or matching found in the previous step, we can find a permutation matrix P1 and a positive number C1 such that A minus C1 times P1 is a non-negative matrix whose number of 0 entries is strictly larger than the corresponding number of A. Therefore, this matrix A minus C1 P1 has fewer non-zero entries. If it has more zero entries, it means it has fewer non-zero entries. Therefore, by induction hypothesis, the induction hypothesis, A minus C1 P1 can be written as a linear combination of permutation matrices, and therefore we get the desired result that A1 is a linear combination of permutation matrices. So that's a recursive procedure to write this matrix, this doubly stochastic matrix is a linear combination of permutation matrices. All right. So let's do now another application, a second application of Hall's-Marriage theorem, which involves a notion of weighted bipartite matchings or weighted transversals. So this sometimes is called, it's also called the assignment problem. And here's how we describe it. So let's say we have a matrix, let's call it W, of weights. Again, it's a square matrix, and is a natural number. So you have this entry Wij, which are greater or equal to 0. Okay. Now you can think about it. You can think of it as in terms of a graph if you want. You can think of it as a graph, again, in which you have these rows, this bipartite graph, row 1, row 2, row n. And you have these columns, C1, C2, Cn. But now you can think of it as a weighted graph in which an edge, let's say from row I and Cj, this edge gets weight Wij. So if the weight is 0, then you can think the edge is not there. Okay. So if you want to, let me give you a matrix W. Let's think about this one. 3, 1, 4, 4, 5. 1, 4, 3, 5, 4, 7, 6, 8, 7, 2, 5, and 6, 3, 2, 8, 7. So in this case, we don't have any zero entries. So you have all the edges between the 5 rows and the 5 columns, and their weights are given in this matrix. Now, what is the problem? So this is a Simon problem, or maximum weight, sometimes called maximum weight transversal problem. What we want, so let's, as before, we have this correspondence between, so a perfect matching in this graph gamma, which I define here. A perfect matching in this graph gamma, it's the same thing as a transversal in W. So what is a transversal in W? This is a set of n entries in W, such that no two are from the same row and the same column. Okay, so as before. Now I will denote the transversal by T. So as before, if I pick, I don't know, let's pick some transversal here, 7, 1, 2, 5, 5. So if you pick this this transversal T, the transversal in that picture, one can define the weight of the transversal, which is the sum of the entries ij in the transversal. So the sum of the weights in that. So this sum, again, you can think of it as a weight of the transversal or the weight of the perfect matching in the bipartite graph. And in this case, it equals what? It's 7 plus 1 plus 2, that's 10, with another 10, it's 20. Okay, so it's clear that there are, at most, I mean, if the entry is 0, if you have some entry zeros in the matrix, that entry 0, well, I guess you can put it in a transversal, but yeah, it won't contribute so much. So there are, you can think of that there are n factorial transversals of W. Okay. So the problem is find a transversal of maximum weight. All right, so this is how we are going to do it. So this is commonly, the procedure that I will describe is commonly known as the Hungarian algorithm. And Hungarian refers to two mathematicians from Hungary, Koenig and Egervary, that have solved problems related to this algorithm. So here's the idea. So to solve this problem, we actually introduce some auxiliary notion. And so that notion is going to be called weighted cover of the matrix W. Okay, so what do we mean by it? So in our situation, we have this this matrix W, this square matrix W, and the entry here, it's Wij, row I, okay, column J. Okay. So what we'll introduce is, we'll introduce for each row, we'll introduce one, we'll have one number, U1, U2, ui all the way up to un. And similarly, for each column, we'll have one number v1, v2, vj, all the way up to vn. And so the collection, so let's say u consists of all these numbers u1, blah, 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 un, and v consists of these numbers v1, vn. So uv is a weighted cover for w if we have the following wij. If I look at the entry in the row I and column j, this is at most ui plus vj for every I and j between 1 and n. So the entry here, wij, is at most the sum of the entry in the row, ui, and the entry in the column, vj. Okay, so yeah, maybe it's not clear what the purpose of it is, but here's the following proposition. And this says the following: for any transversal or matching, let's call it T, and any cover, any weighted cover, UV, we have the following. The weight of the cover is at most, the weight of the transversal is at most the cost of the cover. Now the cost of the cover, CUV, I haven't defined it, but CUV, I'll just include it here, CUV is the sum, it's the sum of all the covers, U1 plus UN plus V1 plus Vn. Okay, so this happens for any transversal and any weighted cover. And this is the first part. And the second part is that we have that the weight of T equals the cover, the cost of a cover CUV, if and only if T is a maximum weight transversal. Okay, so how do we prove this? Well, the first part, it's very easy. You have, so if we take a transversal T, we have that the weight of ij is less than or equal than ui plus vj for any ij in this transversal T. And when you sum up these n inequalities, what do we get? On the left, we get the weight of the transversal. And on the right, because this transversal has the property that there is exactly one entry from each row and each column, we catch all the ui, so it will be u1 plus un, and we catch all the vi's plus v1 plus vn, which is the cost of uv. Okay. Now for the second part, so for the second part, from the first part, what do we get? We get that we get the max-min theorem of the form that the maximum over all T transversals of the weight of T is at most the minimum over all UV covers of the cost of the UV cover. So if we are in the first part, in the second part, so let's say we have this T that attains the maximum. No, we have a T such that we have a T and a cover UV such that the weight of T equals the cost of UV then that means that this weight of t must attain the maximum and this cost of v must attain the minimum. And here we must have actually equality. Okay, so if we have the weight of a transversal equal to a cost of a cover, that is the place where these two universes meet, where the maximum overall the transversal of the weight of the transversal equal the minimum weight minimum cost of a cover. So in that case, so yeah, this is the same. So this weight, so this equality here, it's equivalent to the fact that the weight of ij equals the sum of ui and vj plus every ij in the transversal. And this is the key property that we will look for when we search for, when we're trying to find a maximum weight transversal. So let's do an example on a graph. So of this algorithm. So now I'll describe this Hungarian algorithm. So again, we start with this matrix W. Now we don't have any cover at the beginning, and we have no transversal. So we can start. You start by picking an arbitrary cover. So now it's fairly easy to pick an arbitrary cover. You can choose for the rows ui to be the max entry in row I. And for vj, you can put it to 0. And that's, that's one way. You can switch them around, but that's one cover. It's clearly that this will satisfy wi is less than or equal than ui plus vj for every ij. This is true because ui always beats wij for this for this initial cover. Okay. And now we form a bipartite graph. Which corresponds to this cover. So let's call it gamma UV. And again, the size of the bipartite graph as before. So the rows, the ones on one side correspond to the rows of W, and the ones on the other side corresponds to the columns of W. And now when do we put, if I have a row I and a column J, when do we put an edge between them? So we have that row I adjacent to column J, if and only if you have equality, if and only if Wij equals ui plus vj. Okay, so now that's how the algorithm starts. And the first step is you create this bipartite graph. And now if gamma uv has a perfect matching, now remember this perfect matching is the same thing as a transversal. Let's call it T. Then we struck gold because in that situation we have equality here happening. So we'll have equality happening, Wij equals ui plus vj for any ij in this matching or transversal. So that means that the weight of the transversal is the cost of the cover, and that is the same thing as T is a maximum weight transversal. But what can happen is, so this is the lucky situation, but if not, so if gamma UV doesn't have a perfect matching, then, so by Hall's theorem, it means that there exists a subset of rows such that the neighborhood of S is strictly less than the cardinality of S. Okay, and in that situation, what are we going to do? Well, so we have a collection of we have this matrix W, and we have here some set S, and the neighborhood for it is smaller. This neighborhood of it is smaller, N of S. So now what we do is, for every I in that row S, we are creating a new cover in which UI prime is going to be UI minus 1. And for every J in the neighborhood of S, we create a new cover there, Vj prime, which is Vj plus 1. Now, as you see, on an entry here, Ij, Wij, where I and J, so I is in S and J is in neighborhood of S, then the condition Wij was, from before, it was UI plus, is at most UI plus Vj. But now this is going to be the same thing as UI prime plus Vj prime. So this condition is still satisfied. And for the other parts, the condition will also be satisfied, by a similar argument. So the main point here is that this new cover U prime is a cover of W, but what happened was that the cost of U prime V prime is going to be strictly less than the cost of UV, because we subtracted ones in the set S and we added ones in the set and neighborhood of S, but the cardinality of S is bigger than the cardinality of the neighborhood of S. So what we did is we are decreasing the cost of the cover at each step. And eventually, at some point, so the transversal weight increases, and so at some point this procedure will yield a transversal T and a cover U0 V0, such that the weight of T equals the cost of U0 V0. Okay. So I will give an example at the beginning of next lecture related to this algorithm, but since I'm out of time, I will stop here.